Hey folks, today's topic, sum and difference identities for sine and cosine. So here's the deal. What happens, we know what all the multiples of 30, 45, and 60. We can deal with those. Well, what happens when it's not a multiple of those, like 105? 105 is not a multiple of 30 or 45 or 60. So the sum and difference identities allow us to attack even more of the unit circle. Now it's not perfect. There's still infinitely many angles that we don't have a great system to find an exact answer to, but we can get a couple more added to our toolkit. So these are the formulas. You do not need to memorize these. So if you want to grab your unit circle and add them right away, that's fine. I'm going to add mine right now. So I've got the sine. Now I like to put them together. So notice it says sine alpha plus beta. So alpha is the first angle, beta is the second angle. Now notice the one with the minus, the only thing different in the formula is the plus. So when it's a plus in the middle. When it's a minus in the middle. So this is how I write it. If you want to write them both, go for it. Write them both. There's no problem there. But I'm going to write mine as one combination formula that represents both of them. So it would look like sine of alpha plus minus beta is equal to sine alpha cosine beta. And then what I'm saying here is, well, I'll just write it all first. Plus minus cosine alpha sine beta. So what I'm saying here is when you have sine with a plus, it's going to use the plus. So it's not really plus or minus the way that we think of plus or minus when we do roots. It's more like when there's a plus, you stick with the plus. When there's a minus, you stick with the minus. If you want to write them both out, write them both out. If you don't understand what I'm talking about here, you take the extra 10 seconds, write it out on your own. And then the other one would be cosine of alpha plus or minus beta equals, and now look at the formula for cosine. When cosine, they both go cosine, cosine, sine, sine, cosine, cosine, sine, sine. But when you're adding the angles, you're subtracting the sines and cosines. And when you're subtracting the angles, you're adding the sines and cosines. So I'm going to write mine as cosine alpha plus or minus beta, and then I'm going to switch that order when I get to the other side. So it's going to be cosine alpha, cosine beta, and this is what I mean. When you're doing a plus, this is going to be a minus. When you're doing a minus, this is going to be a plus of sine alpha, sine beta. And again, if you don't understand that, don't do it. Write them both out, write both formulas out, and go from there. All right, so how do we apply these? Now we've got them on our unit circle. We don't have to memorize them in any way. We just have to know how to use them. So evaluate sine of 105. I want to take this 105 and I want to break it up into two angles. Now you can break them up any way that you want, but you should break them up in a way that makes sense. So I could break this up into 100 degrees plus 5 degrees, or 95 degrees plus 10 degrees. The problem with breaking it up in that way, in that manner, is you don't have a special right triangle that fits with 95 degrees and 10 degrees. So I want to always split this up into two nice special right triangles. So that's any of the special rights that you could think of from our unit circle. So what two numbers add together to make 105 from our nice angles? Well, hopefully you figured out pretty quickly that 45 and 60 add up to 105. So 45 degrees plus 60 degrees adds up to 105 degrees. Notice this is still work the same. Sine of 105 equals sine of, and if you add those together, you get 105 again. But now I can take this and I can apply it. Okay, so it's a sine with a plus. So I'm going to use the sine with a plus formula, which means I'm going to plug and chug here. So alpha is 45 degrees and beta is 60 degrees. So this equals sine of alpha, that would be sine of 45 degrees, times cosine. Beta is 60 degrees. I started with a plus, so it's a plus again. Cosine of alpha, which is 45 degrees, times sine of beta, which is 60 degrees. Now you might say, how is that any better than what we had? Well, it's better because we can now turn these into special right triangles. We have a special right triangle. That's the 45 special right triangle. So now over here, I'm going to draw myself a 45-degree triangle. This is a right angle. Reference angle is 45 degrees. Okay, so what are the side lengths? Opposite 45 is root 2 over 2. Adjacent is root 2 over 2. Then I have a 60-degree triangle. So now I'm going to draw my 60-degree special right triangle. Opposite the 60 degrees is square root 3 over 2. Adjacent is 1/2. Once I have my special rights drawn, now I can start to plug and chug from here using my special right triangles. So go to the 45 triangle, boom. Sine is the y, so that becomes root 2 over 2. Times cosine of 60, go to the 60 triangle. Cosine is x, so that's 1/2. Plus cosine of 45, go to the 45. Cosine is x, that's root 2 over 2. Times sine of 60, go to the 60, sine is y, so that's root 3 over 2. From here, I just look at this, follow the order of operations. This is a fraction times another fraction, so we don't need a common denominator. We can just multiply straight across. Root 2 times 1 is root 2. Over 2 times 2 is 4. Plus, then I get root 2 times root 3. Because they're both roots, I can actually multiply what's underneath the roots, and we get root 6. 2 times 2 is 4. At the end of the day, this is a fraction plus another fraction. My math voice is very happy because I've got a common denominator already. So I'm going to write that down first. And then I'm going to think, okay, root 2 plus root 6. Can we combine those? I mean, we combined root 2 and root 3 into root 6. So we should combine. No. This is multiply. Multiply and roots are only one level apart in the order of operations house. They work well together. Add and roots are too far apart. So the best we can do is write square root of 2 plus square root of 6. Now, who knows what that number is? I don't know what that number is exactly, or I mean even estimating what that number is, but it allows us to give an actual answer for sine of 105 degrees. All right, let's jump right into it. Let's have you try example 2. Cosine of pi over 12. All right, let's see how you did. No, cosine of 75 degrees. Sorry, cosine of 75 degrees. All right, let's see how you did. So I'm going to figure out how to break up 75. So I'm going to pick 30 and 45. So cosine of 30 degrees plus 45 degrees. Now what's interesting, if you did 45 plus 30, you're going to get the same answer, but the order is going to be mixed up, and I'll show you what I mean by that in a minute. So this is the cosine formula with a plus. Cosine with a plus, so alpha is 30 and beta is 45 for me. So that's going to be cosine of 30 degrees times cosine of 45 degrees. Now this is where they switch. So in cosine, if it's a plus here, it's a minus here. And then sine of alpha, which is 30 degrees, times sine of beta, which is 45 degrees. Now I need to take those and I need to draw some triangles. So let's use brown. So I need a 30-degree triangle. And I need a 45-degree triangle. .30 opposite is 1/2. Adjacent is square root 3 over 2. 45. That's mama bear for both of them right in the middle. So now we can start to plug in cosine of 30. Go to the 30. Cosine is x, so that's square root 3 over 2. Cosine of 45, that's the 45, that's x, that's square root 2 over 2. Minus sine of 30 would be 1/2 times sine of 45, which would be root 2 over 2. Root 3 times root 2 is root 6 over 4 minus root 2 over 4, which gives me root 6 minus root 2 over 4. Now, let's say that you did 45 plus 30 instead of 30 plus 45. That's fine. You would get an answer that looked like this. Negative root 2 plus root 6 over 4. Actually, no, who would this? No, you'd get the same answer, wouldn't you? Because those are, let me ask you this. How about this? Are these the same answer? Sorry, you would get the exact same result whether you did 45 plus 30 or 30 because these are commutative. But are these the same answer? Yes. So I don't care what order you write things as long as everything has the correct sign. The root 6 is the positive, the root 2 is the negative, and we're both over 4. So like always, we start off by looking at what happens in the world of degrees, and then we add on the world of radians. So this time I want to break up cosine into something that turns out to be pi over 12. I want to break that up into something that's like pi over 6 or pi over 4 or pi over 3. So what I'm going to do is I'm going to choose a number that reduces with 12. So let's add this to our unit circle. Maybe we can put it, because I want to leave this space for the tangent formula. Maybe we can put it up here in this space here. All right, so let's write up all the numbers through 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. What are the numbers that reduce with 12? So in other words, I'm asking you, if I put this number over 12, we could reduce it and get a new value. So 1 over 12 does not reduce. 2 over 12 reduces. 3 over 12 reduces. 4 over 12 reduces. 5 over 12 does not reduce. 6 over 12 becomes 1/2. That reduces. 7 and 12 don't reduce. How about 8 over 12? Does 8, dang it, that should have an X through it, not a circle. Does 8 over 12 reduce? Yes. Now it doesn't cancel, but it reduces because 8 and 12 are both divisible by 2. 9 and 12 are both divisible by 3. 10 and 12 are both divisible by 2. 11 and 12 are relatively prime. And 12 and 12 is divisible by 12. So those numbers that we circled, those are the numbers that we're allowed to pick from to try to build one of our radian measures. And that's because I want to reduce them with 12 so that I get a nicer angle. So in this case, let's look at this and you decide what are the two different ways that you could break down using these numbers to build a 1 out of 12. So in other words, you're trying to build a 1. There's lots of ways. There's lots and lots of ways that we could build a 1. I could do 3 take away 2. I could do 4 take away 3. I couldn't do 6 take away 5 because 5's out. But I could do 9 minus 8 or 10 minus 9. So any one of those combinations will get me to the right number. I'm going to purposefully choose 10 and 9. That's because I want to point out something that I don't want you to fall for when you're on your own. So we're going to do the cosine of, and I'm going to break this into, instead of being 1 pi over 12, I'm going to split it into, what did I say? I want to do 10 and 9. 10 pi over 12, subtract 9 pi over 12. First of all, is that equivalent to what we had before? Is this still the same? Do these have the same value? Yeah, 10 minus 9 is 1 pi over 12. So what's the point? Why did we do this? Because I can now reduce this. Cosine of the quantity, what's 10 over 12 reduced to be? 5 pi over 6. 9 and 12 are both divisible by 3. 3 pi over 4. Now I have two angles that are angles that I can use to build triangles in the unit circle. Here I didn't. Pi over 12, that's not a nice place. 10 over 12 and 9 over 12, I don't know where that is, but once I reduced them, then that allowed me to go ahead and be able to draw some special right triangles. So I'm going to plug and chug first. So I'm using the cosine formula with the subtract. So that's going to be cosine of alpha times cosine of beta. Notice I didn't treat beta as a negative because I'm using the subtract formula. You can't have it both ways. If you want to treat beta as a negative, you can, but then you have to use this as your formula because that's leaving that sum in between. So cosine alpha, cosine beta, when it's a minus, it switches into a plus in the middle. Sine of alpha times sine of beta. All right, now I want to figure out what cosine of 5 pi over 6 is and cosine of 3 pi over 4. I can't do that without looking at their triangles. Okay, so the 5 pi over 6, that's counting by 30s and 5 of them. So where would that leave me? 1, 2, 3, 4, 5 would leave me over here. So my 5 pi over 6 is a triangle that looks like this. My right angle and then my reference angle, we counted by 30s. Cosine of 3 pi over 4. 3 pi over 4, I'm counting by 45s. I'm counting 3 of them. 1, 2, 3. Now I'm going to take that triangle, I'm going to blow it up. Right angle, reference angles of 45 degrees. So now I can fill in the sides of these. A 30 opposite is 1/2, adjacent is square root 3 over 2, but now you see why I picked 10 and 9? What do you got to remember, going back to last unit, negatives matter. So that goes backwards on the x, so that's going to be negative. That goes up on the y, so that's positive. Across from a 45 is root 2 over 2. Adjacent to a 45 is root 2 over 2. Do I have any negatives? Yes, that one's negative. So now I can take these and I can plug them back in over here. Cosine of 5 pi over 6. This is my 5 pi over 6 triangle. Cosine is the x side. Cosine of 3 pi over 4. This is my 3 pi over 4. Cosine would be negative root 2 over 2. Sine of 5 pi over 6 would be 1/2. Sine of 3 pi over 4 would be root 2 over 2. Root 3 times root 2 is root 6. Plus, I already know I'm going to have a common denominator, so I'm going to skip writing out that step. Okay, so question 1 on the homework. I'm going to recommend you use subtract because that's going to guarantee that you're going to get some negatives again. But of course, I won't notice that unless you come up and ask me for some help. But I would really recommend using, instead of doing another example as a group, I'm going to let you double dip and do your next example as one of the homework problems. But I use subtract to make when you break it up. Next time we're going to do tangent. We're going to add tangent to sine, cosine, and then tangent.